Today I wanted to cover some of the kind of misconceptions and some of the mistakes that are made when trying to make an accurate temperature measurement with an RTD. I came up with kind of 5 major ones that I see pretty frequently, and the whole attempt here today is just to kind of raise awareness of these, not necessarily answer all your questions about exactly how to go about correcting them or being able to measure more accurately, but just to kind of raise awareness so that you know what questions to ask of your RTD manufacturer or metrology people, whoever you use to help get an accurate temperature measurement. So we'll start walking through each one of these. If I can get the slides to move here. There we go. First off, I want to go through some definitions, talk a little bit about interchangeability, and then we'll look at several error sources that come into play with RTD temperature measurement. Then we'll look at how to combine all those different error sources to come up with a measurement uncertainty. And then we'll just kind of do a quick review of those same 5 points and maybe a few additional items on how to improve that measurement accuracy. First off, when we look at measurement and error, we probably all know what those are. So I'd throw them out here so that we kind of all be on the same page to begin with here. Where it really gets a little gray is the difference between accuracy and uncertainty. The uncertainty is it's a quantitative measurement where we look at a whole bunch of different error sources and we can combine them using a variety of methods, and we come up with what we call an uncertainty of that measurement. And if you talk to metrologists, that's what they're going to want to do. That's kind of their language. But when we look at, you pick up a temperature probe or a tape measure or something, you wonder, well, how accurate is it? So there's a number there, and they say, here's the accuracy, and it's plus or minus this much. And that's just a little bit not totally correct. And I'm going to try to explain some of that. And what I really like is this beginner's guide to uncertainty of measurement. This goes through in very plain, easy to understand language, talks about the difference between what accuracy is and what uncertainty is, and how to go about creating that uncertainty number for a particular measurement. And the link below here is just an excerpt from that article that talks specifically about accuracy and uncertainty. And it does a really good job of explaining it.
And Bill, just to add to that that kind of document was attached to your registration, so you could have downloaded it when you registered. But if for some reason you didn't, just shoot us an email, and we'll go ahead and get that sent off to you.
All right, good. Yeah, I use that all the time when I'm just as a refresher to myself, because once in a while the details get a little gray. So when we're looking at error sources here, I like to divide these into 2 categories. There's the sensor errors, and then there's the installation errors. Most of the time, the installation errors are by far a lot greater than what the sensor errors are. But first, we'll go through and we'll look at just a handful of the ones that apply to the sensor, and then just a few of the more common error sources with installation. It's certainly not all of them, but these are typically the biggest contributors to an uncertainty measurement budget. So I put these together in a little table. I don't know if, Jeff, are we going to be linking so people can download the presentation also? Is that going to be on the website?
Currently, it won't be on the website, but we certainly can get them in a PDF format, we can get them this table and make that available as well.
Yeah, I don't know. They find it useful just to have these. I just jotted down a few of the ones that I find, kind of the biggest contributors. There's certainly others, but these are what I think are the most important. So what kind of I think the biggest misconception here that I see with RTDs is what's called interchangeability. A lot of times manufacturers don't even mention this. They'll just have in their specs that, well, it's a class A RTD or it's a class B. That isn't the accuracy of the RTD. It's not the accuracy of the measurement. It's just the tolerance band that the manufacturers use when they're building the parts. And the two standards that are followed are this ASTM and the IEC. So they just kind of lay out the groundwork of, kind of the playing field of where, okay, here's kind of what an RTD should do and how it should perform. They're not real stringent, and you're going to find a whole variety of RTD performance that's they all meet the standard, but there's others that far exceed what the standard is. You typically pay a little more for those, but you do get a lot better accuracy, stability, repeatability, those kinds of things. We look at it in a graph form. You can see that at 0 degrees C, which is right here, that's where this interchangeability number tolerance band is the most accurate. That's where the manufacturers trim the little platinum resistor to as close to 100 ohms as they can get. And these are the temperature bands. And now as you move away from 0 degrees C, the tolerance increases. And that's where a lot of the accuracy or uncertainty mistakes are made. And we'll look at a couple examples of how that happens. We can also look at these tolerances in equation format. So if we are looking at this 60751, which is the international standard, probably the most popular one, and the class B is certainly specified a lot. At 0 degrees C, this part of it, of course, drops out. So we're just at plus or minus 0.3 degrees C. But if we were at a different temperature, let's say, minus 85 degrees C, we just plug in that temperature here, drop the minus sign, and that would give us your interchangeability tolerance at that minus 85 temperature. Just a little example here. This one's at 65 degrees C, and this turns out to be plus or minus 0.52 degrees C. Some other error sources, insulation resistance of the probe. This one typically isn't very big, but it can cause a lot of repeatability problems with the probe. So if you were to make a measurement 10 times, you're going to get 10 different readings. And they could be quite different depending on how bad the insulation resistance is. Typically what happens, is just you take a megometer and measure between the probe sheath and the lead wires. And it's typically, in the hundreds of megohms. Sometimes I think the standard specifies 100 megohms as a minimum or maybe it's 200 megohms minimum at 0 degrees. But you'll find that a lot of manufacturers' specs will say 500 megohms at 20 degrees C, room temperature. And here's just to get an idea of the magnitude of the error of this, where, 100 megohms, that's hardly even worth talking about 0.003. But if you get up to, half a meg, 500,000 ohms, it could be pretty significant. So, and it's typically what happens is that moisture will get inside the probe, and it shunts between either the lead wire connections or the little coils of platinum wire, and it provides a little easier, lower resistance path for the electricity to take. So you're going to have a lower than actual temperature measurement. And that moisture moves around a little bit, and it can, and that's where the lack of repeatability comes from. As soon as you start putting electrical power to that coil of wire, it heats up just a little bit, and it can move the moisture around pretty quickly. And moisture is probably, 95+% of the issue with it. Sometimes if there's been some damage to the RTD, that can do it also, but that's pretty rare. Another good error source is long-term stability. In this graph I pulled from a catalog, and it just shows what happens over time. So we have, after 1,000-hour heat soak, 500 degrees C, which was the max rating for this RTD. We're at 3.35 degrees C. This typically would be, an increase in temperature. Not always, but typically would increase the indicated temperature. And if you're down in the, 200, well, less than 200 degrees C, it's almost a non-factor. It's just, it's 0.0 something degrees C, which for most processes is pretty insignificant. Repeatability. The manufacturer should have a specification for this also. And I guess with all of these things, with repeatability and stability and drift and things like that, you should be able to find published numbers for the RTD. If you don't, you may want to consider going someplace else that does tell you what these are, because these are really important, and the manufacturer is the only one that's going to really know for sure how their probes perform. Some of them, are a little more conservative in their estimations based on testing that they've done with these, and some are a little more liberal with it. But it certainly says that they've taken the time to find out how their equipment works and to publish it and say, here it is. Repeatability usually comes in, and it's by usually a number of different temperature cycles over the temperature, the service temperature of the probe. And in this example, it's 0.1 degrees C after 10 cycles. Hysteresis. This one really only applies if your process is heating and cooling more than like 100 degrees C. If it's less than that, this number is going to be so tiny that you really need to pay attention to it. And what this is just it's the error that happens if you heat the temperature probe and then cool it back down, and then at the midpoint of that heating and cooling cycle, you'll have your maximum repeatability difference. So it could be, it could be a 1/10 of a degree, for example, if you cycle between -200 and 500 C. This manufacturer calls it 0.04% maximum. Self-heating RTDs are they're either just a coil of wire or just a little tracing of platinum on a ceramic substrate. So anytime you run electrical current through a wire, it's going to heat up. And it's no different than for an RTD or PRT, which is platinum resistance thermometer. And that's going to give you a higher than actual temperature measurement. So the error source with this, in our example here, we just use the simple equation, the power is the current squared times the resistance. And I've used 65 degrees C again, and we crunch through all the numbers, and we end up with 0.007. So again, pretty small number, and this is just with 1 milliamp of current. So if you had 2 milliamps, that's going to be twice that number. Most transmitters, controllers, PLCs, those kinds of things that RTDs get plugged into are probably around 1 milliamp. I know some transmitters are like 0.8 milliamps. And I've seen some chart recorders, things like that, that they have an option for like a 5 milliamp current, which seems a little ridiculous to me, but they may have the reasons for it. So anyway, something to look at, another little error source that you might want to consider adding to the measurement uncertainty calculations. And I think here, Jeff, are there any questions that we can go through, or shall we just keep plowing ahead here?
Yeah, not at this point, but it's good, a good chance to just a reminder for folks, if you do have a question, go ahead and type it into the Q&A section, and we'll get you an answer kind of on the fly as we go here. So don't be shy. Bill's going through a lot of information here, so if there's something that's unclear or you have a question, go ahead and type it in the Q&A section.
Yeah. Now, time response error. I mean, this is one of those. It's kind of a crossover between a sensor error and an installation error. And I put that first here in the installation error section. It's if you have a process that's changing temperature quickly, and your temperature probe isn't keeping up with it, you can have quite a huge error of several degrees. And if we look at this graph here, this is time and this is temperature. We've got our process heating up or cooling, or in this case it's heating up. And we have our temperature probe here kind of lagging behind it. And we have this huge error source right here. And it can take quite some time for the probe to catch up. And in processes that are steady state, this may not be a very significant error, but if your process does change temperature quickly, this can be a huge error source. So it's something to certainly consider. The next, probably one of the more common error sources I see is stem conduction. And this one, it can be a little bit hard to kind of quantify what it is. It's really related to the immersion depth of the sensor, the style of the sensor, the heat transfer characteristics of the process that you're measuring. If it's something like water, it's pretty easy to measure that temperature. But if it's something that has, like steam or just even air temperature, that can be more difficult because that heat transfer just doesn't happen very quickly. And I've also noted that processes that have, food beverage type stuff that has a higher fat content, I see more stem conduction error with those kinds of things. And it could actually be demonstrated with a cup of coffee, one with black and the other one with cream in it. And the one with cream cools off slower than the black coffee does. It's just that fat content that tends to kind of insulate the fluid, I guess is the best way to put it. The error that we see, it's usually, it's pretty much a direct proportion to the change in temperature. So between the ambient conditions and the process temperature. Of course, if your ambient and the process are the same, then of course there's no stem conduction error. But as that difference grows, the stem conduction gets a lot worse. I can just kind of show this graphically. If we have 200 degrees C fluid in a pipe and a temperature probe stuck in there, there's just going to be a little bit of a chilling effect on the sensing element from the ambient condition, which in this example is 25 degrees C. So if you get enough immersion length, that error goes away. And here's a little graph that shows, and it's kind of hard to see some of these numbers down here. I'll just kind of walk through. So what this test was done with is with this type of an assembly. So it's a tapered thermal well, and it's I think this was a 13.5-inch long immersion probe. And we just took a bunch of data points. And so anything less than, we're at about 4 inches of immersion, there's almost no stem conduction error. And it starts to grow down here at 2 inches, we're maybe a couple degrees C. But then as you get shorter and shorter, of course, it gets worse and worse. So, with this style of temperature probe, you want to have at least 4 inches of immersion to get a good, accurate measurement. And of course, this is in water, so the fluid's going to matter. If it's air, you're going to need more immersion. If it's some other fluid other than water, you're going to require a little more immersion or a different style sensor. Usually, I've done some other presentations on stem conduction, and we go through and look at a lot of these factors in detail. But just as kind of a quick overview here, things like tip-sensitive probes really help insulating the outside of the process. And then again, lean on the manufacturer for help if you're seeing some type of an error. Lead wire error. This is really only applies to 2- and 3-wire connections, and most of the industrial stuff uses either 3- or 4-wire. Very few things use 2-wire except for HVAC type equipment. If you look at an 18 gauge cable, absolute worst case, you got 0.16 degrees Fahrenheit for every 100 feet of that stuff that you use. If we use a 4-wire connection, the transmitters and controllers and things, they can completely compensate for that lead wire error. But if you're stuck with the 3-wire, I put together this little table here. This is the wire gauge. So if we look at 22 gauge, pretty common. And if we have a grade A interchangeability, typically if you go over 15 feet, there's going to be enough variability and resistance between the 3 leads to cause a problem. Then moving on to calibration error, and this is, I was kind of debating whether this is a sensor error or if it's an installation error, but despite having all kinds of fancy equipment and fixed point baths and comparison calibration to a primary temperature standard, there's still an error that comes into play between all of the high-end metrology equipment and the probe that you're using in your process. So this error needs to be included in the our uncertainty calculations. These are just a few of the factors that come into play, even in the calibration lab. Even humidity and the ambient temperature conditions can have an effect on the accuracy of the equipment that's used. And then there are other sources, and these are, they're really specific to the installation. And if you know or can measure a vibration level, that can actually help the manufacturer of your RTDs to define what a potential error might come into play there. There's, if a RTD is seeing a lot of vibration, it tends to start work hardening the platinum coils, and it will cause the resistance to increase over time. And it can be a very small number, and it may take, several years, but that can contribute to that, that drift as the probe ages. If it is severe, it can be as quick as a few minutes or hours or days, maybe months. But so these things are, if you can quantify what's going on, it can help your manufacturer to help you come up with a number to apply to your uncertainty budget. One of the things I wanted to mention with thermal radiation, I had a situation where it was a new installation, and it was a temperature probe that was put into an uninsulated pipeline, a little tubing system, and they validated the system, everything was working fine. They went into production, and all of a sudden that temperature probe is reading a lower temperature than what they expected. And after going through 20 questions with them, we narrowed it down to the fact that somebody had set up a fan close by to keep one of the technicians cool and to move some air around. And it was blowing on that temperature sensor, causing it to cool off and causing some stem conduction and a lower than actual temperature measurement. So it was a real easy fix. You just kind of redirect the fan and it came back up to where it should be. So one of those things that you need to look at all of these different sources of error for your measurement. So what do we do with all of these errors that we've got? One of the easiest ways to combine these and come up with a standard uncertainty is with this root sum square method. So we just take all the error sources, square them, add them together, and then do a little square root. And if we want to do an expanded uncertainty for this 95% confidence level, we just multiply by 2. Just a little example here, again, using 65 degrees C. And I made up some error sources. There was some stem conduction in there. There was, repeatability. There was some vibration going on. And I came up with 0.713. And then if we go through and apply our coverage factor, we end up with plus or minus 1.43 degrees C. And that's at 65 degrees C using a Class B RTD. So, and I just throw this out there just to show that if we look at using just the interchangeability number and say, okay, I can stick that probe in my process, and it's plus or minus 0.3 degrees C. Well, that is like way far away from what reality is. We really need to go through, look at all these different error sources, put them together and do this kind of an exercise to get a good expanded measurement uncertainty number. Now, fortunately, there are ways to improve this kind of a measurement. And in another presentation I did, I go through this in great detail about how we can improve each one of these. And in fact, I think if you go to RTDology on YouTube and just search RTDology, that presentation is in there, and it goes through this in a little more detail. We look at how we can actually calibrate the temperature probe, and that will eliminate a lot of the interchangeability. And we can match that to a transmitter, and that further improves the measurement. And I think in the example, we ended up getting back to about 0.337 degrees C after doing all the things to improve the measurement. So anyway, this is just to raise awareness that interchangeability is not accuracy of that measurement. And we need to look at all of the different error sources that come into play. We need to go through this, combining these errors. And, you know, if you are not comfortable with that and you don't have a metrology staff in the plant, call the manufacturer. I know I do a lot of assistance with this kind of calculations with our customers. Most of the RTD manufacturers can help. If they can't, again, you might want to think about going someplace else. And then the standards for RTDs. These are just kind of the playing field. They're not particularly stringent on the performance, and you're going to find all different levels of performance from different manufacturers. So it does pay to shop around if you're looking for the best, most stable, repeatable, accurate temperature measurement. So with that, I think we're just going to open it up to questions if there are any. And
yeah, we've got some a little bit of time for questions. I know we're a little bit over our 30 minutes, but if there are questions, go ahead and type them into the Q&A section, and we'll get them answered. There are a couple questions. You touched on it a little bit, Bill, but someone was wondering about, are there methods, or what are the methods for mitigating stem conduction error? You maybe just want to run through those again.
Yeah, there are several things you can do. One of the, typically if you go with a smaller diameter probe that has less mass to it, that can help increasing the immersion length. And this can be done with a variety of ways. It might be through a different style piping system where you put in a T, for example, and you stick the probe in the run of the T. That can get you more immersion length without blocking up the flow rate. Probes that are tip sensitive, and sometimes a little heat transfer paste in the very bottom of the thermal well that can help with that, with the thermal conduction and minimize the stem conduction. And one of the easiest ones to do, and in fact makes a really quick test to see if you do have a stem conduction problem, is just insulate around the outside of the temperature probe. It might include, well, I've had people just, take their jacket off or sweater and throw it around the top of the probe, and within, a couple minutes, they see the temperature changing. And then you know that, yeah, this is a stem conduction problem, and we need to look at, either adding some formal insulation around it or changing out the probe type. But those are probably some of the best ways to do it. Sometimes people will just enter an offset into their measurement system. And I guess as long as the ambient conditions stay the same, that's an okay way to do it. If it's in a pretty well, air-conditioned environment, whatever, there's not a lot of, sun shining through windows for part of the day or whatever, then that might be an okay way to do it. But certainly not my preferred. What else?
Okay, and we've got another question on insulation resistance, or IR. If the IR is going down, is my sensor starting to fail? And then that's the first part of the question, and then the second part is, can IR go up, and does that mean anything if it's going up?
Well, typically, if the insulation resistance is decreasing, then yes, the probe is starting to fail. at room temperature, I know we measure them. They have to be, for most of our stuff, it has to be 500 megohms or greater. And if you measure that same probe at its max service temperature at 500 degrees C, you're going to be down at about 20 megohms, which is still fine for an accurate measurement, but the ability of the insulating materials to do their job at elevated temperature, it degrades as the temperature goes up. Now, if you're seeing the insulation resistance get better, what it means is that at some point there was some kind of contamination inside the probe, whether it was moisture or something else. And if you heat up the probe, and if it's a moisture issue, it can drive that moisture out of the probe, and you'll see your insulation resistance increase. Still means that there's a moisture leak in the probe. So, you may want to consider replacing it anyway, but that can be kind of a Band-Aid fix, is just to heat it up for, overnight in an oven to try and dry it out. That's typically done at maybe 150 degrees C. Kind of anything over, 212F or 100 degrees C probably does it pretty well. But again, it still means that there's probably a hole in the probe and it needs to be replaced.
And just the second part of that question, Bill, was does IR ever go up, or is it usually just a one-way?
Yeah, that's the case where it would go up, is if you're drying out the probe, you notice that it goes up.
All right, very good. And then it looks like we have one last question. What determines which standard I should follow? And I think early on in the presentation you had mentioned IEC versus ASTM, and so I think that's what the question is related to. Is there a particular standard they should be following?
It's going to depend on the manufacturer. Some will use the ASTM, others will spec the IEC. The ASTM has a little tighter tolerances than the IEC, but that's really going to be spec'd out by whoever is making the RTD. I know we just historically, we really don't follow either one of them. Our tolerances are just a little bit tighter, and it's because we picked them out before the standards were even around. So we use, for like our Class A or Grade A's, plus or minus 0.05. The standards are written as 0.06, and for the Class B, they're 0.12, and we use 0.1. And for whatever reason, we've not changed to follow the standard. We've decided to just stay in that little bit tighter tolerances for those two classes. And you'll see that with other manufacturers too, especially the ones that have been around a long time. They'll use the 0.05 and the 0.1. I have seen where some are updating to the newer tolerance bands. So it can get a little confusing, but again, lean on the manufacturer. They should be able to help you out with those kinds of questions.
Okay, well, it looks like that's it for questions. So we would like to thank you for attending, and we look forward to seeing you at future events. And as a reminder, we will be posting the recording on YouTube shortly, so you can look for that if you missed something. And if by chance you do have a challenge or an issue that you'd like to discuss further, please give us a call directly. So with that, we hope to see you in future sessions, and have a great day.
All right. Thanks, everybody. Bye now.